based questions on the topic crystal structure. Before going into the topic, I just want to tell you, please read the textbook 2 to 3 times so that you can understand the topic very nicely. Since your upcoming exam is in the MCQ format, so this video will help you in some way to certain extent to understand the topic. Let us begin the topic, crystal structure. Let us see what is matter first. Matter is mainly classified into, as you already know, solids, liquids and gases. And the materials which we are talking here, the matter is composed of, we know that it is composed of atoms and molecules. And if we go into the detailed study of the structure of the atoms, we know that there are nucleons and the electrons revolving round the nucleus. Here nucleon, here I mean it is the protons and neutrons. But in this crystal structure, we are talking about the atoms or molecule. We are not going into the electronic structure. So we will talk about atoms or molecule in the crystallography. And the atoms or molecules in the solid, we know that they are attached to one another with a strong force of attraction. In case of the solid, force of attraction, a strong force of attraction is there, and because of this the solid maintain a definite volume and shape. We know that solid has definite volume and shape, and this shape is because of strong force of attraction between the atoms or molecules. A physics which deals with physical properties of solids, particularly crystals, including the behavior of the electrons in them, is called as solid state physics. Depending upon arrangement of atoms or molecules, the solids are mainly classified as crystalline solid and non-crystalline solid. Very important. The word which is appearing in the bold, they can ask as fill in the blank or true or false. So solids are mainly classified as the crystalline solid and non-crystalline solid. Crystalline solid consists of regular and periodic arrangement of atoms or molecules. So we know that crystalline solid means the regular and periodic arrangement of atoms or molecules. So the word which is appearing in the bold format, there is a chance they can ask in the fill in the blank or true or false format. In any way they can ask. They have different properties such as thermal conductivity, electrical conductivity, refractive index, etc. in different directions. And they also have sharp melting points. Most of the solids are crystalline in nature, and the examples of the crystalline solids are salt, mica, quartz, copper sulfate, calcite, diamond, etc. On the other hand, amorphous solid consists of irregular arrangement of atoms or molecules. Amorphous solid means the molecules and atoms are not arranged in a regular or periodic pattern. It is the irregular arrangement of atoms or molecules. And the periodicity, if exists, extends for a few atomic diameter only. If there is no periodicity is found in amorphous solid, but if there is a periodicity, then to a certain atomic diameter it will be there, and that is a short range order. Amorphous solids have same physical properties in all directions, whereas the crystalline solids do not have physical properties in all directions. It is a direction dependency, as I already told. But here the amorphous solids have same physical properties in all directions. That is, it is isotropic. The solid do not have sharp melting. These solids, this amorphous solid here, I mean, do not have sharp melting points. And the example of amorphous solids are float, glass, rubber, plastic, etc. Crystalline solids are further classified into single crystals and polycrystalline solids. In single crystals, the periodicity of the atoms may extend throughout the material, as in diamond, mica, quartz. So we should remember that the periodicity of the atoms may extend throughout the material. Here they can ask fill in the blanks based on the line which is appearing in the bold format. A polycrystalline material is an aggregate of number of small crystallines with a random orientation, separated by well-defined boundaries. Again, they can ask fill in the blank or true or false based on this line. These crystallines are called as grain and boundary. The periodicity of the individual crystalline is interrupted at the grain boundaries. Very important to note that it is interrupted at the grain boundary. These materials are more stable as compared to single crystal forms, and some of the metals and ceramics are polycrystalline in nature. In the blank based on this they can ask metals and ceramics. Some of the metals and ceramics, they are polycrystalline in nature. Every crystal consists of a regular and periodic arrangement of atoms. As I already told you, crystals means there is a periodic arrangement of atoms or molecules. If these atoms or molecules are replaced by the points, now we are not going to talk about the atoms or molecules, here we will simply say the points, then an array of points is obtained, as we used to get in Rangoli. There, when a lady used to put some Rangoli in front of the house, she first put some regular arrangement of dots and later on she make a beautiful picture. So say similar way, if the atoms or molecules are replaced by the points, then an array of points is obtained. This regular and periodic array of points such that the environment around each point is identical, means the environment, there you can see the repetition. If you look into any of the point, you can see identical points, and there you can see the repetition. And if such environment around each point is identical, then we can say that it is called as a space lattice. It is nothing but the space lattice. Fill in the blanks as well as true or false based on this, or multiple choice question can also be asked based on this slide. The figure, in this figure you can see the dots, and it is a regular periodic arrangement. And this point here, I just told dots, it is nothing but the points. This point is nothing but atoms or molecules. This point represent atoms or molecules, and these points are called as lattice points. Very important, these points are called as lattice points. There you can see OA and OB. OA and OB are the two axes along which the separation between two consecutive points are represented respectively A bar and B bar. They are called as unit vectors. Very important, they are called as unit vectors. It is called as unit vectors or primitive vectors. Another name for unit vector is primitive vectors. The space lattice is an array of points in space such that each point has an identical surrounding. As we already talked about this, if we are talking about any particular point, and when we look into its neighborhood, we can see that each point has an identical surrounding in crystal. But in crystal, we should note at the same time there is a geometric arrangement of atoms and molecules. And if we want to represent crystal structure with the help of the lattice, then each point must be associated with an atom or molecule. As we already told here, this point represents the atoms or molecules. The atoms or molecule associated with a lattice point is called basis. Very important. They can ask to fill in the blanks based on this line. And it acts as a building unit or a structural unit. This basis acts as a building unit or a structural unit for the complete crystal structure, and this we can say as it is a form of a brick. With the help of brick, we can construct the entire building. In the same matter, this basis is acting as a building unit or the structural unit for the complete crystal structure. Hence, space lattice plus basis will give you the crystal structure. Means when we combine space lattice with the basis, we will get the complete crystal structure. Thus, lattice combined with basis generates complete crystal structure. Space lattice plus basis will give you the crystal structure. Here in this diagram you can see lattice plus basis. When these two get combined, you will get the crystal structure. Sometimes they may give you the diagram and they will ask you what is this. So remember this is a lattice, basis and crystal structure diagram. The parallelogram in two-dimensional lattice and the parallelepiped formed by the translation vectors A bar, B bar and C bar in the three-dimensional lattice can be considered as the fundamental building block for the construction of the complete lattice. Such as smallest geometrical units, by the repetition of which a complete crystal structure can be formed, is called as unit cell. Very important, unit cell. Fill in the blanks based on this line they can ask you. The figure shows unit cell of three-dimensional lattice with the side represented by primitive vectors A bar, B bar and C bar. As you can see, A bar, B bar, C bar is the primitive vectors. Another name for the primitive vector is the unit vector along the crystallographic axis X bar, Y bar and Z bar respectively. The angle between these crystallographic axes is represented by alpha. You can see alpha between Y and Z, beta between Z and X, and gamma between X and Y. The intercepts A, B and C, which define dimension of unit cell on the respective crystallographic axis, are called as primitives of unit cell. The fill in the blanks can be asked based on this. The three primitives A, B and C are three identical angles. Gamma, alpha, beta and gamma together are known as lattice parameters. Very important, these are called as lattice parameters. Lattice parameter defines the shape and size of a unit cell. Primitive vectors A bar, B bar and C bar along the crystallographic axis X bar, Y bar and Z bar respectively. The angles between three crystallographic axes represented by alpha, beta and gamma are called as interfacial angles. Very important, this word interfacial angles, they can ask in the blanks based on this line. The intercept A, B and C, which define dimension of a unit cell on the respective crystallographic axes are called primitives of unit cell. Again, fill in the blanks based on this line they may ask. The three primitives A bar, B bar and C bar and the three interfacial angles alpha, beta and gamma together are known as lattice parameters. Again, they can ask fill in the blanks or true or false based on this line. Lattice parameter determines shape and size of a unit cell. Again, true or false based on this line, there is a chance they can ask you. A unit cell formed by primitives A, B and C and which has only one lattice point is called as primitive cell. Very important, one lattice point is there and then it is called as primitive cell. Whereas a unit cell having more than one lattice point is called non-primitive unit cell. Very important, it is called as non-primitive unit cell. Smallest volume enclosed by the normal in the primitive cell, such a cell is called as Winger-Seitz cell and its volume is given by V is equal to mod A bar dot B cross C. Very important, the volume of the cell, such a cell is given by V is equal to mod A dot B cross C. Numerical based on this they can ask you. Now we quickly see symmetry operations. Before going into symmetry operation, first we should know certain things, that is geometrical symmetry is observed in most of the crystals. Very important, geometrical symmetry is observed in most of the crystals. The operation by which crystal and its environment remains invariant is called as symmetry operation. Very important, under symmetry operation the crystal and its environment remains invariant. And there are two kinds of a symmetry operation. One is point group and second is phase group symmetry. While the symmetry operation made by the translation is called as phase group symmetry. Translation, phase group symmetry. Rotation, reflection and inversion are the fundamental operations of point group symmetry. We will see one by one. Rotational symmetry, when a crystal lattice is rotated about an axis by a certain angle and the lattice appear to be identical to the lattice before its rotation, it will remain the same. In such case, the lattice is said to have the rotational symmetry. And the angle by which when we rotate and it remains the same, the angle it is given by phi is equal to 2 pi by n, where n can be 1, 2 and 3. The integer n is the multiplicity of the axis of rotation. In all the lattice of a regular polygon cross section, there is rotation symmetry. This is important, you should know. Integer n is called the multiplicity of the axis of rotation. In all the lattice of a regular polygon cross section, there is a rotation symmetry. And if there are n sides of a polygon, Then we know the formula phi is equal to 2 pi by n. If there are n side of polygon, there will be n times rotation symmetry in one round. That is, there will be n fold symmetrical rotational axis. These words are very important. In a lattice, only 1, 2, 3, 4 and 6 fold symmetry is possible. So you should remember these numbers. 1, 2, 3, 4 and 6 fold symmetry is possible. Here in the diagram, here it is example showing a rotational operation. The rotation of a body of a triangular cross section by an angle phi, and here the phi is equal to 2 pi by 3. When we rotate it through 2 pi by 3, we will get the same condition as before the rotation. And after rotation by 2 by 3, the crystal appears just like the prior to its rotation. And hence here it is the threefold rotational symmetry. It is the threefold rotational symmetry. Reflection symmetry, as the name indicates, we will see the reflection. A lattice is said to have reflection symmetry about a plane if it is left unchanged in a way after being reflected in the plane. After the reflection, it remains unchanged. The reflection symmetry in a lattice is possible if a plane is drawn in the lattice such that it divides the lattice in exactly two identical parts, so that one part can be obtained as a reflection of the another. In the upcoming diagram, it will be clear. So remember this. A lattice is said to be reflection symmetry. When it is said to be reflection symmetry, when about a plane, if it is left unchanged in every way after being reflected in the plane. Figure show the reflection, how after the reflection the object appears. Diagram show the inversion. The lattice possesses an inversion symmetry if for every point given by the position vector r, there is a corresponding lattice point at the position vector r bar. This diagram indicates the inversion symmetry. The shape of a crystal structure depends upon the size and shape of a unit cell in the dimension, in the three-dimensional lattice. On the basis of different values of A, B and C of unit cell and the angles alpha, beta and gamma between the faces, the crystals are classified into very important 7 systems. The crystals are classified into the 7 systems, that is cubic crystals, tetragonal crystals, orthorombic crystals, monoclinic crystals, triclinic crystals, trigonal crystals and hexagonal crystals. We are going to see each crystals one by one, but very important on the basis of the different values of A, B and C of a unit cell, and also the angle alpha, beta and gamma between the faces. The crystals are classified into 7 important systems. Remember the number 7. Cubic crystal. In cubic crystal system, the lattice parameters A equal to B equal to C, and also alpha equal to beta is equal to gamma is equal to 90 degrees. Under this category, 3 types of lattices are possible, that is simple cubic, body centered and face centered. And for simple cubic, the symbol is given by SC, body centered BCC and face centered FCC. And lattice symbol for simple cubic is P, body centered is L and face centered is F. Side of a unit cell are equal and each side is mutually perpendicular, that is A equal to B equal to C. And also alpha, beta and gamma, here the value of alpha, beta, gamma for the cubic crystal is equal to 90 degrees. Tetragonal crystal, here A equal to B but not equal to C, and also alpha equal to beta is equal to gamma is equal to 90 degrees. Under this, Bravais lattice can be simple and body centered, and common abbreviation for this simple is ST, and for body centered it is BCT, and lattice symbol is C and L. Here you should remember and learn this lattice parameter for tetragonal. They can ask fill in the blanks based on this lattice parameter. Two sides are equal, but the third side is comparatively longer and sides are mutually perpendicular, means A equal to B but not equal to C. Here alpha, beta and gamma equal to 90 degree for this tetragonal system. Now we will see the orthorombic system. Orthorombic system, here A is not equal to B is not equal to C, and alpha equal to beta is equal to gamma is equal to 90 degree. Very important, this lattice parameters very important, you should learn this. All three sides are equal, but the three axes are mutually perpendicular to each other, means A is not equal to B is not equal to C, and the alpha, beta and gamma is equal to 90 degree for this orthorhombic system. Rhombohedral or trigonal system in which A equal to B equal to C, but alpha is equal to beta is equal to gamma, but they are not equal to 90 degree. Three sides of the unit cell are equal and the three axes are inclined to each other by the same angle but not perpendicular. So here in this condition for the rhombohedral or trigonal system, it is A equal to B equal to C, but alpha is equal to beta is equal to gamma, but it is not equal to 90 degree. They are not perpendicular to each other. Hexagonal system. In hexagonal system, A equal to B but not equal to C, and at the same time alpha is equal to beta is equal to 90 degree and gamma is equal to 120 degree. This you should remember. Two sides of the unit cell are equal and the two axes are mutually perpendicular, while the third axis is inclined at an angle of 120 degrees. That is A equal to B but not equal to C, and alpha is equal to beta is equal to 90 degree, whereas gamma is equal to 120 degree. Monoclinic crystal. In monoclinic crystal, A is not equal to B is not equal to C, and alpha is equal to gamma is equal to 90 degree, but it is not equal to beta. This you should remember. Three sides of the unit cells are unequal and the two sides axes mutually perpendicular, but the third axis is inclined, that is A equal to B not equal to C, and alpha is equal to beta is equal to 90 degree, and gamma and not equal to beta. Now we are going to see the triclinic system. In triclinic system, A is not equal to B is not equal to C, and whereas alpha is not equal to beta is not equal to gamma is not equal to 90 degree. Sides of unit cells are unequal and all the three axes is inclined, that is A equal to B equal to, A is not equal to B is not equal to C, and at the same time alpha is not equal to beta is not equal to gamma, and this is not equal to 90 degree also. We will see Bravais Lattices. In 1984, a French crystallographer named Auguste Bravais suggested that there are only 14 independent ways of arranging point in three-dimensional lattice such that the environment about such points remain identical. Here you need to learn this 14 independent ways such that the environment about each point remain identical. Thus, amongst the 7 crystal systems, 14 different space lattices are possible, are called as Bravais lattices. Again, multiple choice question based on this line they can ask. Either it can be true or false, or it can be fill in the blanks. So remember this line, very important line. Unit cell. Remember this 4 lattices, which is very important: simple or primitive lattice, body-centered lattice, face-centered lattice. You are familiar with this 3, and the 4th one is base-centered lattice. In simple cubic lattice, there is one center or atom or point at each corner of the unit cell, and this is called a simple cubic cell or P-cell. Simple cubic or primitive cubic lattice. In simple cubic lattice, each lattice point, this point represent atom or molecule, so lattice point is shared by 8 unit cells, and each unit cell share 1/8 part of the lattice point. This the words appearing in the yellow color is very important from fill in the blanks point of view as well as from the true or false point of view. Remember, students. So for the simple cubic, one lattice point is surrounded by 8 unit cells, or 8 unit cell shares 1/8 part of, each unit cell shares 1/8 part of the lattice point or atom. Now we will see number of lattice points or atom per cubic cell. Average of lattice point or atoms per unit cell is equal to 1/8 multiplied by 8 is equal to 1. Again, multiple choice based on this slide can be asked. Now we are going to see the coordination number of simple cubic lattice. In simple cubic lattice, there are 4 lattice points in the same plane and 2 in vertical plane, 1 upward or 1 downward. At a distance r equal to a from any lattice point, Hence, total number of atom nearest to an atom in a simple cubic crystal is the coordination number, and in the simple cubic the coordination number is 6. Atomic radius. For a simple cubic, the atom in a unit cell touch along the side of the cell. If A is the lattice constant, then radius of the atom is given by R is equal to A by 2. Remember this from MCQ point of view. Packing fraction or packing density. Before going into the details of the packing fraction of simple cubic, we will first see what is the packing fraction means. The packing fraction is defined as the fraction of space occupied by the atom in a cubic cell. It is the space occupied by the atom in a cubic cell. It is given by APF, atomic packing fraction, is equal to number of atoms per unit cell multiplied by volume of the atom divided by volume of the unit cell. So APF is equal to Z times 4 by 3 pi R cube upon A cube. Remember this formula from MCQ point of view, as well as numerical based on the slide can be asked. Packing fraction or packing density in simple cubic, number of atoms per unit cell n is equal to 1. Radius of the atom R is equal to A by 2. Therefore, APF is equal to 1 into 4 by 3 pi A cube upon B square divided by A cube is equal to pi by 6 is equal to 0.52. Therefore, void space is equal to 1 minus APF is equal to 1 minus 0.52 is equal to 0.48. This number is very important. Void space is equal to 48%, whereas APF is equal to 52%. Body centered cubic lattice. In body centered cubic lattice, in addition to one center at each of the 8 corners of the unit cell, there is one at the center, one atom at the center of the unit cell. It is also called as F cell. Unit cell consists of one atom or lattice point at the each corner and one atom at the center of the cubic cell. The contribution of 8 lattice point at the corner of the cell means 8 into 1 by 8 is equal to 1. And the lattice point at the center of the cell belong to the cell itself. Hence, average number of lattice point or atoms per unit cell is equal to 1 plus 1, which is equal to 2. Atomic radius. For the atomic radius, first you should understand the diagram says. So, diagram, one atom is at the center, whereas at the corner 8 atoms are there. And when we consider the diagonal, then the then the entire atom consists of R plus 2R plus R will give you the entire length of the diagonal. So AG square is equal to AC square plus CG square. When you solve, you will get R is equal to radius is equal to root 3 by 4 times A. Therefore, atomic radius in B.C is equal to root 3 by 4 times A. Remember, this number is very important from numerical point of view, as well as they may ask the formula. So you should be thorough with the formula for the atomic radius of BCC, which is equal to root 3 by 4 times A, or otherwise they can give you the value of A and they will ask you to find the atomic radius. So either way they can ask, in number of ways they can ask the MCQ based on the slide. And now we are going to see the packing fraction of body centered cubic lattice, or the packing fraction, or another name for the packing fraction is the packing density. In BCC lattice, number of lattice point or atoms per unit cell is equal to 2, and the radius is given by R is equal to root 3 by 4 times A. When we will substitute, we will arrive APF is equal to 0.68, that is 68%, whereas the void space is equal to 1 minus APF is equal to 1 minus 0.68, which will give you 0.32, means the percentage void is equal to 32% void. Now we are going to see the coordination number of body centered cubic lattice. In body centered cubic lattice, the central lattice point or atom is surrounded by 8 equidistant neighbors at a distance root 3 A by 2, and hence coordination number of BCC crystal is equal to 8. Remember this 8 number for body centered cubic lattice. Now we are going to see the face centered cubic lattice. In face centered cubic lattice, there is one center lattice point per atom at each of the 8 corner of the unit cell, and one center lattice point per atom at the center of each of the 6 faces of the unit cell. It is also called as F cell. In FCC lattice, the unit cell consists of one atom at the corner and one atom at the center of each of the 6 faces of the unit cell. Hence the contribution of 8 lattice at the corner on the unit cell, that we are going to see first, that is 8 into 1 by 8 is equal to 1. And the lattice point at the center of each face is shared by the 2 adjacent unit cells. Hence the contribution of 6 face centered lattice to the unit cell is equal to 6 into 1 by 3, which is equal to 3. Hence the average number of lattice point or atoms per unit cell is equal to 1 plus 3 is equal to 4. Remember this, average number of lattice point per unit cell for the face centered cubic lattice is equal to 4. Face centered cubic lattice. अब हम उसमें कोऑर्डिनेशन नंबर ऑफ फेस सेंटर क्यूबिक लैटिस देखने वाले हैं. जो येलो कलर में जो भी है दैट इज़ वेरी इंपॉर्टेंट, उसे याद अच्छे से रखेंगे. जो भी स्लाइड्स में मैंने डिफरेंट कलर यूज़ किया है दैट विल बी द चॉइस, मल्टीपल चॉइस क्वेश्चन के आंसर्स ये रहेंगे. क्वेश्चन कैसे भी रहने दो बट द आंसर विल बी दैट, सो बी केयरफुल. और जो येलो कलर में मैंने किए हैं वो सब आंसर अच्छे से याद कर लेंगे. तो इन FCC लैटिस द डिस्टेंस बिटवीन नियरेस्ट लैटिस कितना रहेगा, a/√2. ये जो a/√2 है वो भी वन ऑफ द MCQ क्वेश्चन का आंसर हो सकता है. वेयर a इज़ द लैटिस कांस्टेंट. इफ a इज़ द रेडियस, a/√2 is drawn taking center as a face centered lattice point, then there are 12 lattice point. कितने lattice point होने के chances है, 12 lattice points होंगे और atoms on its surface. Hence coordination number of a face centered cubic cell क्या रहेगा, 12. very important, coordination of a face centered cubic cell is equal to 12. मैंने जहाँ जहाँ येलो कलर करके रखा है दैट इज़ द इम्पॉर्टेंट आंसर, क्वेश्चंस के आंसर. मोर एवर बहुत सारे न्यूमेरिकल्स पूछ सकते हैं. यहाँ पे उन्होंने सिर्फ a की वैल्यू दे दी है 1.5 एंड दे कैन आस्क यू फाइंड आउट हाउ द डिस्टेंस बिटवीन द नियरेस्ट लैटिस. वो ऐसे पूछ सकते हैं डिस्टेंस बिटवीन नियरेस्ट लैटिस फॉर फेस सेंटर्ड क्यूबिक लैटिस फाइंड आउट करना है वेयर a इज इक्वल टू 1.5. तो तुम्हें जल्दी से आंसर आना चाहिए. डिस्टेंस बिटवीन नियरेस्ट लैटिस है a/√2, तो उसका आंसर आएगा 1.5 डिवाइडेड बाई √2. लाइक दिस न्यूमेरिकल्स, इस चैप्टर में न्यूमेरिकल्स बहुत सारे पूछे जा सकते हैं. Atomic radius of face centered cubic cell, as you can see from the diagram, and when we will calculate we will arrive to radius is equal to a/2√2 for the face centered cubic lattice. Remember this, r is equal to a/2√2, and the atomic radius of FCC is equal to a/2√2. They can give you the value of a and they will ask you to find atomic radius of FCC, or they can ask you to tick the correct option for atomic radius of FCC. So either a number of multiple choice questions can be formed based on this slide. Packing fraction or packing density in FCC crystal, number of lattice point or atoms per unit cell is equal to 4. Therefore, r is equal to a/2√2. When we will substitute in a value in the formula of APF, we will arrive to the value 0.74. APF, atomic packing fraction, is equal to 0.74, that is 74%. And if we are going to find the void, then void is equal to 1 minus APF is equal to 1 minus 0.74, which is equal to 0.26, that is 26% void. Now we will quickly see the density of the material. Density is calculated by rho is equal to mass of unit cell divided by volume. That is number of atoms per unit cell into mass of each lattice point atom divided by a cube. Rho is equal to z into m upon a cube. Rho is equal to z m upon n times Na upon a cube, where m is the molecular weight of the crystal and that is Na is the Avogadro's number, and rho is equal to z m upon Na a cube. Remember this formula. They can ask you to find a numerical based on this. They can ask you, in the above formula there appear one term z, and for the simple, if they are asking for simple cubic, then substitute z is equal to 1. For BCC it is z is equal to 2, and FCC it is z is equal to 4. Miller indices, I will not go into details of the Miller indices, but remember students, numerical question based on the Miller indices, they are going to ask. So you should thoroughly practice Miller indices a lot from numerical point of view. The crystal lattice is considered to be made up of parallel and equidistant plane passing through the lattice point. These planes are called as lattice planes or crystal planes. In crystal, unlimited number of crystal planes with different possible orientations are present. The perpendicular distance between the two consecutive lattice plane is called as interplanar distance or lattice interval. In a crystal, to represent the lattice plane with respect to crystallographic axis, Miller gave a method for crystal plane representation by using a set of three integers h, k and l. These three integers, which are used to describe the orientation of the crystal plane, is called as Miller indices. You should practice, dear students, you should practice this Miller indices thoroughly, because they are going to ask, surely they are going to ask numerical based on this. Miller indices are defined as a reciprocal of intercept made by the plane on the three rectangular axes. Once again, Miller indices is defined as the reciprocal of intercept made by the plane on the three rectangular axes. And the method for finding the Miller indices is, first get the intercept. First you need to find the intercept. Then you are going to find the reciprocal of that, and after that you find the LCM of the denominator of this reciprocal. Then multiply each reciprocal by LCM and make it a full integer. These number HKL are the Miller indices such that HKL is equal to 1 upon P is to 1 upon Q is to 1 upon R. Lattice plane, this figure diagram you should learn, because 1 0 0 how they appear. So 1 0 0, here you can see 1 means it is touching the x-axis. Remember this diagram, 1 0 0. Now the Miller indices for 0 1 0, this diagram you should remember. Here for 0 0 1, how the diagram looks. This slide indicates 1 1 0. This slide indicates 1 0 1. This slide shows 0 1 1. This diagram gives 1 1 1 representation. This figure gives 2 0 0 representation. 0 2 0, 0 0 2, 0 3 0 representation. 1 2 0, 2 2 2, 1 2 1, 2 1 0, and 3 2 1. Dear students, these figures are very important. Maybe they will give you to find which one is correct. For example, they will ask and they will give you 0 3 0, and they will give you the diagram, and they will give you multiple choices as 0 0 1, 1 1 1, 0 3 0, 2 1 0. So you should correctly take the diagram, which diagram it is showing. So from numerical multiple choice question, these diagrams are very important. You should learn this thoroughly. These are the Miller indices of the planes in a cubic system, and maybe they will say to find 0 1 1. So you should correctly take which diagram is showing 0 1 1 plane. That is very important. So do not ignore these figures. These figures are very important, and learn figures and also their indices, the Miller indices. Also the Miller indices is very important from numerical point of view. So practice from the textbook, whatever numericals they gave you, they practice a lot so that you can score very high marks. All the best students. Bye.